Alright, in this video we're going to look at showing p of x is equal to the sum of I guess I'll call it I of ai from 0 to n x to the n. We want to show that this as well as q of x defined similarly for, let's call it j from 0 to n of bj x to the j. That should be an I here. That should not be an N. There we go. So we wanted to show that indeed this result is a vector space. Okay. So the first thing we need to show is the sum of p of x plus q of x non-equals, which is equal to the sum of each of these terms. Well, if we expanded this out, a0 plus b0 plus a1 plus b1 x plus dot 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 is still going to be a polynomial. Call it a to the n plus b to the n x to the n. It's still going to be a polynomial of degree n with coefficients from whatever field we're pulling out of. So it is definitely closed under addition. Similarly, if we multiply, let's say p of x by some constant, let's say a is probably not going to, let's try c, then this is very much going to be c times a naught plus c times a1 x plus dot 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 plus a and c x to the n. So it's still going to be a polynomial of degree n, so it's closed under scalar multiplication. Okay. For the next one, if I reverse the order and I wrote this as q of x plus p of x, that would be no different than writing it as above, plus the sum of these two things. The only difference is the order of the terms would be different, but since these pull from the field where they're commutative under addition, it doesn't affect the overall structure, and so they are commutative under the operation of addition, polynomial addition. For part D here, if we look at p of x plus q of x plus some other polynomial function r of x, and we want to know if that's equal to p of x plus q of x plus r of x. Okay, so if we are looking at whether or not we add the first two polynomials, q of x and p of x and q of x together, and then add r of x, or if we add p of x and after adding q of x and r of x together, we will arrive at the same value, or the same polynomials. Again, these are inherited properties from the field in which we're pulling the elements from, so the associativity just does hold as well. The zero polynomial, so p of x plus zero polynomial, in other words, where all of the a's are 0, is going to be the identity, and that will then lead us to the value of p of x. So this one also checks. I guess I should put checks on all the others since we have that. And then the additive inverse definitely holds, since p of x, if we add negative p of x, those two will result in identifying the identity of 0. So the additive inverse of p of x is indeed negative p of x. And if we consider two multiples, c times d times p of x, this is exactly equal to c times d of p of x. Again, inherited from the field in which it's pulled from. So this is identically equal to the associativity of whether we multiply two numbers together and then multiply it by the constant or by the polynomial, or if we multiply one number times the polynomial and then multiply another number by the polynomial, the result will end up being the same. So that checks. Likewise, if we add two constants, we multiply it by p of x, that's the same thing as c times p of x plus d times p of x, meaning that the, I don't know why I have it over the c there, meaning that the polynomial distributes over the sum of two numbers as well. And the multiplicative identity of 1 times p of x does in fact return the exact polynomial. So again, inherited from before, so it does in fact have that same connection. Okay, all right, let's move on to the next example. In the next example, we want to look at the all matrices. So A is equal to some m by n matrix, and B is equal to some m by n matrix. Okay, so if we go through the same set of things, A plus B is well defined matrix-wise. It's component-wise, so it is indeed closed. If we add two matrices of the same size together, we'll get a matrix of the same size because you're doing it element-wise. Part B. Multiplying C times A is still a matrix where each of the elements get multiplied by the value of C, which is still of the same size, so it's still within the, so this also checks. It's still closed under scalar addition. A plus B is equal to B plus A. It's the matrix addition is commutative under matrix addition is commutative. So we inherit that from the property, and also A plus B plus C is equal to A plus B plus C. So if we add A and B together first and then add C, or if we add A and then B and C together, we end up with a matrix that is exactly the same in both situations. There is a matrix such that when we add it to it, it's the matrix where all of the elements are 0. Again, because we're doing this element-wise, you get 0 plus each of the elements of A, and so this is exactly equal to A. And then also, if we add the opposite of A, this will reduce us to the additive identity matrix, which is 0, where all of the components of this matrix are 0. And likewise, for two scalars C and D, if we multiply that by A, that is exactly the same thing as C times D times A. In other words, if you multiply, kind of like up here, right? If you multiply this by a scalar and then multiply by another scalar, it's the same thing as if you multiplied the two scalars together and then added it, or multiplied the matrix by that scalar. So that definitely checks. And we do know that matrix multiplication is distributive, so this could be the same thing as if you want to add those numbers together and then multiply, it's the same thing as if you multiply each of the elements by the individual scalars and then add the two corresponding matrices together. And last but not least, so that checks. The identity matrix, whatever size that may be, if you multiply it by A, you do in fact get back exactly A, so that also checks. So this is exactly what we expected, a vector space. Okay. All right, moving on to the third example. This one, we had something that looked like this. We had a vector called it O plus B, and that's going to equal A to the B. And we had K times O multiplication A, and that was equal to Ka. Okay, so we want to show that this is a vector space. So if we look at the addition Okay, this is a real number, so that checks, which is in the same form. And then Ka is also a real number, so that checks. Okay, if we look at O plus B, which is equal to A to the B, and then we look at B, O plus A, this is equal to B to the A. But this implies that addition